Welcome to the next tutorial in electric circuit analysis. In this tutorial, we will focus our discussion on magnetically coupled circuits. We are going to solve few problems. So problem number 1 is given a circuit with the self-inductance given by L1, which is the self-inductance of the primary part of the circuit, which is 0.4 Henry. The self-inductance of the secondary part of the circuit, which is having a value of 2.5 Henry, and the coefficient of coupling given by 0.6. Given that the current I1 in the primary circuit is 4 times the current in the secondary network, and the value is 20 cos of 500t minus 20 degree. So the current is given in milliampere as the instantaneous value, because with a change in the current, with a change in the time, the current will change. So the instantaneous current equation is given to us. We have to determine the voltage at time t equal to 0. So at time t equal to 0, what is the voltage in the primary network, and the total energy which is stored in the system at t equal to 0. So what is the total energy stored and what is the voltage that we have to determine given the dot connection and the current direction. So we can see that both the current are entering the dot. It means the mutual inductance induced voltage will be positive in nature. So we will see the solution. First, we are going to determine the mutual inductance, which is given by K, that is coefficient of coupling, with the square root or the geometric mean of L1 multiplied with L2. That is the self-inductance of the primary network and the self-inductance of the secondary network. The coefficient of coupling is given to us 0.6 and the self-inductances are 0.4 and 2.5 respectively, which gives us 0.6 Henry as the value of mutual inductance. We know from the KVL equation that the sending end voltage, that is V1, is equal to the drop of voltage due to the self-inductance in the primary network, which is given by L1 di1 by dt, and the mutual inductance with a positive sign because both the current are entering the dot, and here we will be having the current 2 component for we are going to determine the voltage 1. So we have to find the voltage at time t equal to 0. So voltage at time t equal to 0, we can substitute the values of the self-inductances, mutual inductance and the voltage drop. So given the relationship between the voltage and the equation of the self and the mutual inductance induced voltage, we can find out that the primary voltage is 1.881 volt. Now at time t equal to 0, what is the value of the current I1 and I2, which is obtained from the relationship of the current I1 and I2 in the time domain. So we can find that 18.79 and 4.69 millihenry are the current at time t equal to 0. Now we can find out the energy at time t equal to 0 given the relationship of the energy with respect to the inductances as half Li square, that is given the self-induced energy plus the mutual induced energy is Mi1 I2. So we will get 151.2 microjoule as the total energy which is stored in the coupled network when the two inductances are mutually coupled to each other. Next problem. In this figure, the coils have self-inductance of 40 millihenry and 5 millihenry and the coefficient of coupling is 0.6. Current I1 and voltage 2 we have to determine, which are the function of time t, given the voltage 1 is 10 cos omega t and the current 2 is equal to 2 sin omega t. The frequency is given to be 2000 radian per second. So we have been marked the dot at the extreme end of the inductances where the current I1 is entering the dot and the current I2 is entering the non-dot position. So the mutual inductance induced voltage will be negative. Let us see the solution. So first we are going to determine the value of the mutual inductance from the relationship K under root L1 L2, which will comes to be 8.4853 millihenry, and the values of the reactances due to the individual inductance values and the mutual inductance values. We know the frequency of the system is 2000 radian per second. So we can use that to find out the reactance. So we know that reactance X is equal to omega L with J as the direction. So we will get the self-inductance and the mutual inductance for the network. Now we can obtain the network in the form of the impedances marked as shown, and we can write the mesh equation in the loop 1 and loop 2. So the first KVL equation will be given in the mesh 1 and the second KVL equation will be given in the mesh 2. Here we can see that there is a negative in the mutual inductance induced voltage because both are opposing in each other. Now given the condition that the voltage 1 and current 2 which are given to us, we can put it in this KVL equation or the mesh equation, and we can find out the values of I1 and V2 in the phasor domain. So once we have found out the current and voltage in the phasor domain, we can convert that in time domain by using the frequency element. So here we have minus 90 degrees, so we have sine of omega t. Here we have 24.99 degree, so we have cos of omega t plus 25 degree. With the maximum amplitude is 0.5493 and 22.065. Problem 3. Given a network where we have to determine the voltage V0. So V0 is basically the voltage drop across the 1 ohm resistor, and the different elements are shown in the network and the mutual inductances are also given to us. So we have to find what is the potential V0 across the 1 ohm resistor. So first we will mark the current I1 and I2 based on the direction which are suitable to us, and then we can write the KVL equation in mesh 1 and mesh 2. We can find that the current 1 is entering the dot in mesh 1 and current 2 is also entering the dot in mesh 2. So we will have the plus value for the mutual induced voltages. So we have plus value and we'll get the first equation and the second KVL equation in the two loops. Now we can form that in the form of a matrix and we can solve the unknown variables which are I1 and I2. In this case, we need to find the potential V0. So the current I2 multiplied with the resistance 1 ohm will give the potential V0. So after determining the current I2, we can find the potential V0, which is from the Ohm's law, current multiplied with the resistance, which comes to be 540.5 angle 144.16, and the value is given in millivolt. Next problem, here we have to determine the potential Vx. So potential Vx is across the 2 ohm resistor which we need to find out. And we have been given the network on the primary side and the secondary side with a mutual inductance of J1 ohm. So first we can minimize the network with the help of source transformation, where we can apply the source transformation in this part to obtain the values of voltage and the reactance in series, so that the current source is replaced with the voltage source. Once we have done that, we can mark the direction of the current I1 and I2 in the two meshes. So marking that, we can find out that in primary circuit the current is entering the non-dot position, whereas in the secondary circuit the current is entering the dotted position. So the mutual inductance will be negative. Now we can write the KVL equation in the mesh 1 and mesh 2, where we will have the negative value of the mutually induced voltage, and then we can convert that in matrix form and obtain the solution. So the current 2 we have to find because we need to determine what is the potential Vx, which is current 2 multiplied with the resistance of 2 ohms. That will give us 2.074 angle 21.12. Let us see the next problem, which is problem 5th. Here we have to determine the L equivalent in the network. Since this network is involving the mutual inductance, it would not be easy directly to find the L equivalent simply by adding or using the series parallel concept. And we have not been given the frequency component also. So omega is also not given to us. Then in that case, what we can do is that we can assume that omega is 1 radian per second, and we can connect one source of a known source of 1 volt at the input terminal, and then we can convert the each value of the inductance in the reactance form. Because the frequency is 1 radian per second, there will not be change in the values, only the reactance will be obtained. Now, since 1 volt is connected at the input and I1 and I2 are the two mesh current which are flowing, we can write the KVL equation in the two loops, and we can solve to determine the source current I1, which will be originating from the 1 volt source. We know that the input impedance is basically the input voltage by input current. Here the input voltage is 1 volt and the current is I1, which will give us the net reactance XL or XL equivalent. Now, from that we can find out what is the L equivalent value by taking the inverse, and it will give us 7.11 Henry as the net L equivalent of the entire network. Problem 6. Here in this network, the load which is connected at the secondary of the mutually coupled winding is basically a 15 millihenry inductor, and the impedance of the load is also given to us. So we have been given the value of L and we have been given the value of XL. This is given just to find at what frequency we have to operate the system. We have to determine the input impedance of this network under the condition that coefficient of coupling is 0.6 between the primary and the secondary side. So we have to first obtain what is the frequency of the system using the relationship from the load side. So we find that the frequency is 2667 radian per second from the relationship of reactances of the load. Once we have found out what is the frequency, we can convert these inductances values in the reactance form using the coefficient of coupling. So coefficient of coupling will give us the mutual inductance, which is 11.384 millihenry, because both L1 and L2 are given to us, and then with respect to omega we can convert them in a reactance form. So the individual parameters will be converted to reactance in ohms, and then we can find out the input impedance of the network, which is nothing but you will be having on the primary network. If I consider this one as R and this one as XL, then if the mutual inductance is not there, then we can say that Z input is equal to R plus JXL. But due to the mutual inductance, there will be a reflected impedance which will be coming from the secondary side having the mutual inductance. So that value will be given by this relationship, which is omega square m square divided by the net reactance of the or net impedance of the secondary side. This is the impedance of the primary side, which is given by R plus JXL on the primary side, and this is ZR, which is the reflected impedance coming from the secondary side. So we have discussed this in the theory class in detail, how this reflected impedance is coming from the secondary to primary. So we can obtain the input impedance of this network using the formula of the reflected impedance. Next problem, where we need to determine the current I0, which is flowing in the 10 ohm resistor, and the coefficient of coupling is given to us from the primary to secondary inductor, so we can find the mutual inductance. However, in this problem, it is not given what is the frequency of the system. So we have to apply some tricks to find out what is the frequency of the system. So first we will try to reduce the network using the concept of source transformation. So this part of the network we can reduce with having a current source in parallel with a resistance, with a voltage source in series with a resistance, using the concept of source transformation that we have studied. Now what we can do is, we know the relationship of mutual inductance and self-inductance with the coefficient of coupling. In this problem, we have not been given the value of omega. So we have to develop some method by which we can take the omega into account. So in this relationship, if we multiply omega on the both sides, then we can find out the relationship what is to be 17. The 17 ohms is basically the net reactance due to the mutual inductance. Now we can apply the KVL equation in the mesh 1 and the KVL equation in the mesh 2, and we find that the mutual induced voltage will be negative because of the direction of the current entering the dot and leaving the dot. Now we can find what is the current I2 flowing in the secondary of the winding, and current I2 is nothing but the current I0, which is the variable to be determined. So we can get 1.516 angle 92.04 as the value of current I0, which is equal to I2, and this will come from solving these two equations, which you can put it in the matrix form and find out the unknown variable. Here one point has to be noted, how we have used the concept of omega multiplying on both the side of the mutual inductance to find the value of the reactances. In the problem 8, we have to find the input impedance. We have seen in the previous problem where we have used the concept of reflected impedance. However, here we will not use that concept of reflected impedance. Rather, we are going to solve by connecting 1 volt at the input side. So 1 volt if we connect at the input side and mark the current I1 and I2 which are flowing in the individual meshes, then we can write the KVL equation in the two meshes, and on solving these two KVL equation we can find out what is the current I1 which is originating from the source. So input impedance is nothing but input voltage by input current, where input voltage we have taken 1 volt. So it is nothing but the inverse of the current, which is coming to be 9.219 angle 79.9. In this case, because this capacitor was present in the network, we have not gone by the concept of reflected impedance, because otherwise we have to use different formula. So it is better to go with 1 angle 0 to find the input impedance. Next problem, where we need to determine the current I1, I2, I3 which are flowing in the different branches of the network, and the total energy stored in the coupled coil at the time 2 millisecond given the frequency as 1000 radian per second. Mutual coupling coefficient is given to be 0.5. So first we will apply the source transformation so that we can reduce the network having a current source in parallel with a resistance to a voltage source in series with a resistance. We have to apply the KVL equation, and that is the reason we are doing this type of transformation where we required only the voltage source. Now we can use again the concept of omega m from the mutual inductance relationship, because omega is not given directly in the problem. So we can find that the mutual inductance reactance is equal to 5 ohms, and we can apply those in the mesh equation 1 and 2 to find the KVL equation and the unknown variables I1, I2 and I3. So I1, I2 and I3 are the unknown that we have to find out. However, these two equations 1 and 2 we have written in terms of the mesh current I1 and I2. Whereas the branch current I3 is nothing but the difference of the current I1 minus I2. So here the current I1 and I2 indicate the mesh current, whereas I3 indicate the branch current that we can find out from the mesh current. Now the current I1 and I2 which are in the phasor domain, we can convert that in the time domain part with appropriate angle which are involved, that is 72.18 and minus 97.48 with the maximum value of the current I1, I2. Given the frequency is 1000 radian per second. So at time t 2 millisecond, we can put it in this equation where we will have 2 radian, because we have 1000 t involved here, which is equivalent to 114.6 degree, which we can put it in the relationship of the current I1 and I2. Now we can obtain the current I1 and I2. But remember here, these values will be converted to radian and then only the cosine will be obtained. We should not take this in degree, otherwise the mistake will come. So we will obtain the current I1 and I2 at time t equal to 2 millisecond, and then using the concept of omega L1, which is 10 ohms and omega is 1000, we can obtain the value of L1 and L2 separately, which is 10 millihenry, and mutual inductance is 0.5 L1, which is 5 millihenry. So these values are required because we need to find what is the total energy of the coupled coils given by the relationship of half Li square term for the self-inductance and mutual inductance Mi1 I2 with a negative sign, because the current are not appropriating adding the flux, rather that is opposing the flux. So we will have the energy as 43.67 millijoule in the coupled network. Next problem, we have to find the total inductance of 3 coupled coils. So we have 3 coupled coils. Here we can see of each values of 6 Henry, 8 Henry and 10 Henry. We have to note the position of the dot, how it is present and how the current are entering or leaving the values. Now, in order to find the total inductance of these 3 coupled coils, we can solve by 2 different methods. First method is that we can individually obtain the coil total inductance L1, L2 and L3 minus the mutual inductances values which are present in the network with appropriate sign convention, seeing the direction of the current, whether it is entering the dot or whether it is leaving the dot. So we can find the values of the coil 1, coil 2 and coil 3, and then we can add all to find the total reactance or total inductance LT at the terminal. So here we are finding the total L equivalent or LT. However, there is one more method which will be taking the concept from here only, but will not go coil to coil basis. Rather, we will add all the self inductances and we will take 2 times the mutual inductance values with appropriate sign convention. So M12 is the mutual inductance between the first coil and the second coil. M23 is the mutual inductance between second to third, and M12 is the mutual inductance from first to second. We are using appropriate sign here, seeing the direction of the current, whether it is entering or whether it is leaving the dot. So it will give the same answer what is given by the first method. Next problem, which is the last problem of this tutorial, where we have 3 loops involved. So the number of equations will be more. We need to determine the current I2 in the second loop, and given the input voltage is 8 sine 720t. So 720 is basically the frequency of the supply, and all the reactances, all the inductance values, we have to convert that in reactance, and we have to see the dot position and the current, whether it is entering the dot or whether it is leaving the dot, because the positive and negative sign will be involved in the voltage values. So first what we are going to do is we will take the frequency to be 720 radian per second, and we will obtain the new network, which is the X reactance values. All the inductance values will be converted to reactance values with the help of the frequency 720 radian per second. Now we can write the mesh equations in the 3 individual loops with appropriate sign conventions. So here we can see the dot position in the 2 inductors and how the current are entering or leaving the dot in order to write the KVL equations. So in the first equation, which are involving the current I1 in 1.8 ohm resistor, and in this inductance there are 2 current involved, that is I1 and I2, whereas the third coil is coupled with the first coil. So even the coils are not touching, but mutual inductances are there. So we have to take into account the voltage drop due to the reactances. So we have to individually write the equations 1, 2 and 3, which are the KVL equation for the loops 1, 2 and 3 where clockwise direction of the current is assumed. So appropriately we have to take the direction of the voltage drop. Now we can convert that in matrix form where the known currents I1, I2 and I3 we have to determine. So on solution we can find the current 2 I2 which is to be found so in phasor form which is 3.132 angle 57.22 degree, and then we can convert that in time domain with a frequency 720 radian per second and the maximum value is 3.132 which angle 57.2. So this complete the tutorial on mutually induced coupled coils, and together with the theory we have to study this so that we can understand the concept well. Thank you for now. See you in the next lecture.